Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE. Yeah, today we are discussing about even and odd signals. Yeah, already we know that a signal is said to be even or symmetric when it is satisfies the condition where x of n is equal to x of minus n. So here, yeah, a signal is said to be odd or asymmetric when it is satisfy the condition x of n is equal to minus x of minus n. Using this all condition, that you can decide that all either even or odd signal. Signal is available. How we are deciding the factor? The factor is either the signal is even or odd. That time we require that in mathematical where x of n is equal to x of minus n, x of is equal to x of minus n, where x of n is equal to minus x of minus n. Okay, say for example, let's say x of n is equal to sine of n. Here, the x of, if it is x of minus t is equal to minus sine of n is equal to minus x of n. Like this, we can interpret this one. We can change this all mathematical analysis. Okay, so now therefore sine of n is odd function. Due to this all where x of minus t is equal to sine of minus n is equal to minus sine of n is equal to minus x of n. So that is a direct deciding factor, since therefore sine of n is the odd function. So like this, to decide the factor, either function or maybe even or odd signals. Okay, next example, let x of n is equal to cos of n, where here the cos of n, so where x of n is the polarity change here, where x of n is equal to cos of minus n is equal to cos of n is equal to x of n. So here, therefore cos of n is even function. Okay, so every signal x of n, here we can decide that where x of n is normally either it is a continuous time signal or a discrete time signal. Here we are concentrating is here continuous time signal. Every signal x of n can be expressed as a function, as a sum of even and odd components. Okay, within this components, even signal component, where it is followed by where x of xc, it is using that all what do you call even signal. Due to this all even signal, x of n, xc of n is equal to of what do you call x of n plus x of minus n. Yeah, consider here the odd signal component, where we have to consider that odd signal x of the odd x of n, where x of n, x of 0 of n, okay, is equal to of x of n minus x of n minus n. So here we will consider that where x of n is equal to that even signal component and odd signal component. We can combine these two two components to consider that where x of n is what you call every signal, it is followed by x of n, where x of n can be expressed as the sum of even and odd components. Okay, like this, a signal is said to be even when it is satisfy the condition x of t is equal to x of minus t. Here, best example where t2, t4, t5, t3, and so on is the cos t, and so on. Let us x of t is equal to what do you call t2, x of minus t is equal to minus t of into 2 is also equal to t2 is x of t. Therefore, t2 is t2 is the even function. So that means a signal is said to be even when it is satisfied the condition. The condition is satisfied, x of t is equal to x of minus t. Okay, so best example here. So as for this, how they are agreeing, how we are deciding the factor. So rectangular function x of t, there is a rectangular function x of t is equal to where here x of t, or we have to consider where x of t is equal to x of we call x of minus t. So it is also even function. So using this order, a signal is said to be odd when it is satisfied the what you call condition x of t is equal to minus x of minus t. Okay, like this graphically it is observed that all t versus x of t. Okay, here from this origin here 0 t t by 1 or t by 2 t by 3 and so on according to t value in the positive or negative direction where it is. The signal is said to be the odd when it is satisfied the condition. The condition is x of t is equal to x of minus t. Okay, next using the same thing, what you call rectangular function x of t is equal to x of minus t. So it is also even function. The signal is said to be odd when it is satisfied the condition x of t is equal to minus x of minus t. So like this here where t comma t3 t3 and so on t4 and sin t, let consider that x of t is equal to sin t, where x of minus t is equal to sin of minus t is equal to sin minus sin t or is equal to x of minus t. Therefore that x of minus t what you call is equal to sin of minus t. Okay, sin of minus t is also equal to that minus sin time is also equal to what you call minus x of t. Therefore that sin of t here, this value, the sin t what you call is odd function. Okay, therefore sin t is odd function. Okay, so like this the signal is said to be even when what do you call this value. Okay, next coming to the periodic and periodic signal. Signal is said to be periodic if it is satisfy the condition where x of n is equal to x of n plus n. We can decide that our n value where here it is x of n, where x of n is equal to, this is the condition, x of what you call n plus capital N. You can decide here where n is equal to what value initially, the 0, 1, 2, 3 and so on. We can decide that what you call capital N value. Okay, so of that what you call, if it is the signal is satisfied condition, the signal is said to be periodic if it is satisfied the condition x of n is equal to what you call x of n plus n. The signal is said to be periodic if it is satisfied the condition x of n factorial is equal to x of n plus small n plus capital N. Okay, where here this condition capital N is equal to fundamental time period. We know that where capital N is fundamental time period. So reciprocal of this fundamental time period, it is followed by 1 by n, is also equal to what you call that capital 1 by n is equal to what you call that f. Okay, that f is, you know that where f is fundamental frequency. Okay, so therefore where capital N is fundamental time period, so where reciprocal of that capital N is equal to f, that f is the fundamental frequency. Okay, we can decide this the signal is said to be periodic if it is satisfied with the condition. The condition is x of t is equal to what you call x of t plus x of small t plus capital T, or we can consider that x of n is equal to what you call where x of n is equal to x of n, okay, x of n small n plus capital N. Okay, so like this you can decide the factor. We know that all small n value or capital N value. Here that capital T, we know that one fundamental time period. Reciprocal of this fundamental time period 1 by capital T. Okay, So how it is varies that. So the above the signal variation t versus x of t. So like this here it is t naught is identified. Here it is by using positive peak and negative peak. Like positive going transitions to negative going transition. Like peak, positive peak and negative peak. Or peak to peak. This is on cycle. You can consider this t. Yeah, next cycle positive peak and negative peak. That is peak to peak. Positive peak to negative peak. One more cycle t1 and so on. Okay, like here you can decide the tunnel factor. The signal is said to be periodic if it is satisfied with the condition where x of t is equal to x of t small t plus capital T, or we can consider where x of n is equal to x of small n plus capital N. So like this, the signal is said to be the periodic and aperiodic. Okay. Now a signal is said to be a periodic signal if it has a definite pattern and repeats itself at a regular interval of the time. So whereas the signal which does not have the regular interval of the time is known as a periodic signal or maybe non-periodic signal. This is in terms of what you call definition and in terms of the description. But here we have to concentrate on this mathematical expression for this periodic and a periodic signal by using different conditions. The conditions in terms of periodic and aperiodic already it is, we have seen that. Yeah, periodic signal. Yeah, the signal. So the periodic signal, how we are defining this periodic signal? The signal is considered to be a periodic signal. How we are considering the periodic signal? Because of that condition. Based on that condition, the signal is considered to be a periodic signal when it is repeated over what you call cycle of the time or what you call regular interval of the time. Like this, in terms of the definition, the signal is considered to be a periodic signal when it is repeated over cycle of the time or regular interval of time. Okay, so this means periodic signal repeats its pattern over the period. Okay, so like this, the function f of x can be periodic if it is satisfied by following the equation. So you can decide the factor either periodic and aperiodic. Here by using this all f of x plus p, where you can decide that f of x plus p is equal to what you call f of x, where f of x is the what you call f of x, where the function f of x can be periodic if if it is satisfied with the condition. The condition is f of x plus p is equal to f of x. Okay, like this the periodic and aperiodic will be satisfied. Now coming to this, you can consider one example. The cosine signal is periodic. How it is a periodic cosine signal with reference to periodicity value of 2 pi. So we can consider this positive periodic signal. Previously we know that our periodic and what you call positive going transition. Here this is the positive going transition, positive peak and negative peak. But here also the cosine signal is periodic. The periodicity value of the 2 pi. The periodicity value of the 2 pi is assigned what you call, so with reference to the composite periodic signal. Okay, so as you can observe there is this value, simple periodic analog signal, sine wave or cosine wave cannot be decomposed into a simpler signal. This is one way. Other way is the composite periodic analog signal is composed of multiple sine waves. So you can represent this all are the depicts typical composite periodic signal is observed in the positive going transition or negative going transition. Okay, so that means using this simple example, the cosine signal is periodic, periodicity value of 2 pi. Okay, next here also we should consider the periodic signal Yeah, the time domain decomposition, the composite signal. A simple periodic analog signal such as sine wave or cosine wave cannot be decomposed into what you call simpler signals. So for this, the composite periodic analog signal is composed of multiple sine waves. Here it is how many sine waves are there. This is the first sine wave. Okay. Second sine wave, we also what you call blue color is also sine wave. One more sine wave. And black color, one more sine wave. That means we can decide the factor this one and what do you call this one, or we can decide this one. Three sinusoidal signals are there. Based on the frequency, time versus the amplitude, because of that frequency of the blue color, the frequency is 3f, where in what do you call the black color frequency is 9f. Okay, so that means the composite periodic analog signal is composed of multiple sine waves. The figure depicts typical composite periodic signal. Okay, that means if the frequencies varies. Okay, like this time, in terms of this time, the decomposition, the frequency domain decomposition of the composite signal, where t versus amplitude, where initially that frequency is decided, this value. Okay, and 3f, 3f is it is assigned here. Okay, and 9f maybe this color. Okay, like this. So the signal, a frequency frequency domain composition of the composite signal, it will appear like this. If its time domain decomposition of the composite signal is appeared with that what you call frequency, different frequency variation. Okay, is you can observe that the simple periodic analog signal such as sine wave or maybe cosine wave cannot be decomposed into what you call simpler signals. So if it is a composite periodic analog signal is composed of multiple sine waves, you can observe this all graphical representation of either periodic and either time domain and frequency domain. Yeah, in a time domain and frequency domain, they are in the x-axis is the time and y-axis is the amplitude. You can observe that what you call it is in frequency domain decomposition of the composite signal as well as time domain decomposition of the composite signal. Okay. Yeah, here the period, consider the same periodic signal, the time domain decomposition of a composite signal. So here the frequency decomposition, what do you call domain decomposition of the composite signal with reference to this. So the frequency is rate of change with respect to time. This is one aspect. Other thing is that we have the frequency and period or inverse of each other. Hence, the following can be limited, can be implied. So, due to this, where f is equal to that reciprocal of the time period, where t is equal to reciprocal of that frequency. Here it is mentioned where we know that all f, where f we know that one. Reciprocal of that f is equal to where f is equal to 1 by t. Okay, if you want to this, like if you want to calculate the time, this value, t value, where t is equal to reciprocal of that f frequency. Okay, like this, with reference to both time domain and frequency domain. The units such as the seconds and milliseconds, we can consider maybe microseconds, nanoseconds, and what you call picoseconds are used for time period, while what you call units such as hertz, kilohertz, or gigahertz, or megahertz, terahertz are used for frequency. So using this all different value, different frequency variation, how it changes the time domain and frequency domain. Okay, so we'll observe this case. Okay, so the figure depicts the time domain and frequency domain decomposition of the composite periodic signal, which is right observed in graphically. Okay, within this, so this is the derived from the fact that a complete sine wave in the time domain, the complete sine the time domain analysis Okay, then this and can be represented by a single spike in the frequency domain. Single spike, here it is, single spike is the sign. That's why we are considering this one. This is derived from the fact that the complete sine wave into the time domain can be represented by one single spike in frequency domain. Okay, where it is useful, where what are the merit and demerits we will observe in terms of the manipulation of the signal or digital signal processing applications, we will verify. Okay, now coming to this energy and power signals. A signal is said to be an energy signal when it has finite energy. You can represent in mathematically that finite that energy signal E infinity is equal to integral minus infinity plus infinity x of t mod square into dt. The signal is said to be a power signal when it has finite power. P infinity is equal to limit t tends to infinity 1 by 2t integral minus t to t mod x of t square into dt. So we can collect that a signal said to be a power signal when it has finite power. That means we have P infinity is equal to limit n tends to infinity, okay, n tends to infinity, okay, 1 by 2n plus 1 summation small n is equal to minus n 2 plus n mod x of n or square. So energy and power signal will be estimated by using this all mathematical analysis. Okay, using this all mathematical formulas or expressions, you should write the piece of code using the MathWorks or MATLAB. User can verify that energy and power signals how it is varies in graphically. Okay, energy and power signal. The energy of the signal x of n is defined as E is equal to the summation n is equal to minus infinity to plus infinity x of n square. If this energy is finite, that is 0 less than E less than infinity, then x of n is called an energy signal. For signals having the infinite energy, the average power can be calculated, which is defined as P average is equal to limit n tends to infinity, that 1 by 2n plus 1, the summation small n is equal to minus capital N to capital N mod x of n square. Or we can consider power average that what you call having the infinite energy. The average power can be calculated. P average is equal to limit n tends to infinity 1 by 2n plus 1 into En. So where that En is, we know that En value, signal energy of x of n, okay, over the finite interval. So suppose you have to use this particular interval minus capital N less than small n less than or equal to capital N, that is finalize that energy is D is equal to limit n tends to infinity En. Like this, energy and power signal will be estimated in mathematically. Okay, energy and power signal. A signal with the finite energy is an energy signal. Due to this, EF is equal to integral minus infinity plus infinity mod f of t all square into dt. A signal with finite and different from zero power is a power signal, where power is, we know that power is the time average. We can consider the mean of this squared signal amplitude. That is the mean square value of f of t. Like this, the p of n will be calculated. So there exists signal for which neither the energy nor the power are finite. So with the help of where PF, the PF, what do you call, PF is equal to, okay, that 1 by t. You can apply the limit to t tends to infinity. Here we can consider that a minus capital T by 2 plus T by 2 mod f of t with the whole square into dt. There exist signals for which either the neither the energy nor the what you call power or finite. Okay, like this unit step signal. Yeah, now coming to this elementary signals, already we have seen that elementary signal, but it is somewhat it is varies that are unit step signal useful for the representing the causal signal. Sometimes we call the causal casual signals or non-causal anti-causal signals that I would consider under elementary signal with reference to that unit step signal USS unit step signal useful for the representing the causal signal where u of t is equal to 1 t greater than or equal to 0 0 t less than 0. Okay, the discrete time unit step signal u of n is defined as u of n is equal to 1 comma n greater than or equal to 0 0 less than 0. Okay, ramp signal ramp signal is denoted by r of t and it is defined as r of t. Here r of t is equal to 0 if t less than 0 where what you call t by t naught f that what you call 0 to use that limit 0 less than or equal to t less than or equal to t naught. So okay, where r of t where r of t is equal to what you call if it is 1. Okay, yeah, if it is 1. Okay, so the t greater than t naught. Like that ramp signal is denoted by r of t and it is defined as r of t. So area under the unit ramp unit is we are right to verify graphically t versus r of t. Where t is substituted where t is equal to 0, 1, 2, 3, 4 and so on. Where r of t is defined according to your condition where r of t is equal to if it is 0 if t greater than 0. Okay, if it is t by t naught. Okay, if 0 less than or equal to t less than or equal to what do you call t naught. Like this r of value is substituted with like this rate of the area and unit ramp is unity. Okay, where u of t is equal to r of t by dt. Okay, under elementary signals unit impulse function is denoted by delta of t. Here integral minus infinity plus infinity delta of t into dt is equal to u of t. You know that. So from this case u of t where delta of t is equal to derivative of u of t by dt. Within this impulse function is denoted by delta of t. Okay, so here the discrete times impulse function it is followed by delta of n where if what do you call the delta of n is equal to okay where it is 1 if where n is equal to 0 otherwise like this discrete DTS discrete time impulse function whether it is where delta of n where delta of n may be a continuous time signal or delta of n is discrete time signal. Based on the signal time impulse function it will varies. Okay, discrete time impulse function will be decided that what you call if 1 if n is equal to 0 otherwise 0 otherwise. Okay, like this there is a relationship between elementary signals. Okay, already we have seen that all elementary signal if it is delta of n is equal to u of n. Okay, u of n minus u of n minus 1 using this where v of n is equal to what do you call the summation k equal to 0 to infinity delta of n minus k. Okay, so like this where if it is u of n is ready to where n is equal to where n is equal to 0, 1, 2, 3, 4, and so on. So that u of n versus, so u of n1, you can decide the factor, where u of n minus 1, okay, where u of n minus 1, where in this case, like this it will varies, where u of n minus u of n minus 1. So that means it will appear here, this area and this area, that samples are this. Yeah, similarly that u of n is equal to summation k equal to 0 to infinity delta of n minus k. Okay, where delta of n, it is, compare this u of n and delta of n, and delta of n minus 1 and u of n minus 1, and delta of n minus 2, and what you call delta of n minus 1, n minus 2, and so on. So you can compare that relationship between elementary signals will appear in either samples are reflected or not. Elements are reflected or not from both the elementary signal, either it is unit sample or non-uniform samples. Elementary signal, if you are consider rectangular signal or triangular signal, let be denoted as x of t. Let be denoted x of t here. Both cases, the rectangular and what you call triangular. I think so. Both are same, but here it is involved that rectangular. Here somewhere it is added the rectangular rect of r by capital T. But this case, where triangular, where a into 1 minus, what you call 1 minus mod small t by capital T. Okay, using this all. Okay, that small t versus x of t, small t, the small t versus x of t, we can decide the factor, what you call a within t. Okay, the t value 1 minus small mod small t by capital T. So that's why here the triangular signal will be appear. Similar case here, where x of t is a into small r by capital T, small r by capital T. So where it is, where t is based on the t value, based on this x of t value, so that area, that x of t rectangular signal will be appeared. Okay, so using these all mathematical expressions, rectangular and triangular, go on writing that all built-in or inbuilt function using the MATLAB, you can verify the same graphical representation of this. Yeah, it is only for manual operation, but in practical also we will try to verify by using this all inbuilt or built-in function. Based on that, we can observe that a graphically rectangular signal as well as triangular signal. Okay, like this CTS. Next, come to CTS, CTSS and DTSS. Continuous time sinusoidal signal, discrete time sinusoidal signal. We know that all continuous time signal, it is followed by where x of t is equal, it is the continuous time signal, and we know that one, it is followed by CTS, continuous time signal, where x of t is, you know that one, a into what you call cos omega naught into t plus pi. Okay, like this. If it is a discrete time signal, where discrete time signal it is what you call represented, where x of n, it is depending upon this parenthesis, x of t is x of n, where x of n is equal to a into cos of not, okay, small n plus pi. Okay, so due to this continuous time signal, what do you call continuous what do you call continuous time sinusoidal signal, and discrete time sinusoidal signal. Okay, it will appear the CTSS and DTSS, continuous time signal continuous time sinusoidal signal versus discrete time sinusoidal signal. Okay. Now coming to this concept of the digital frequency and discrete what do you call discrete time system definition. A discrete time system is anything that takes a discrete time signal as input and generates a discrete time signal as a. So that means you have to consider the discrete time system is anything that takes a discrete time signal as input and generated discrete time signal as output. So it is appear. The concept of a system is very general. That it may be used to model the response of an audio equalizer or the performance of the what you call like US economy or present what you call India economy. Okay, so digital frequency is in digital signal processing. Yeah, in DSP, normalized frequency is followed by F is what you call quantity having dimensions of frequency expressed in units of cycles per second. You know that all. Okay, using this all, it equals, so where F is equal to F dash is equal to F by Fs. Here in this case, where the F is an ordinary frequency quantity in cycles per second. Okay, and what do you call? Where Fs is the sampling rate in sampling per second. Okay, so this a discrete time system. We are talking about only discrete time system. So where it is coming from this all, it is also coming from this what do you call already it is continuous time signal and discrete time signal. The signals are available. How we are manipulating these all signals? So we require that the system is available. So input is ready to given that either continuous time signal or maybe discrete time signal. Okay, so we will expect that our output response. Okay, a discrete time system is anything that takes a discrete time signal as input and generated discrete time signal as output. Okay, so the concept of the system is very simple, like it may be used to model the response of an audio what do you call equalizer. So we can observe that all other aspect there. Okay, so like this here, continuous time and discrete time systems. In the continuous time signal, despite that having the different physical origins, if you are in the R and C, so where if the Vs is input, can connect this all resistor and capacitor, right, to verify that Vc of t. Okay, where Vs of t, it is splitted that what you call in terms of the mathematical variation. Okay, so where x of n, where this x of n, what you call it is, we can consider the real time aspect. This where x of n is monthly deposit, we can deposit something here. So invest account to 1% monthly return and monthly balance where we can consider the y of n. So normal cases wherein the input is Vs of t, how it is expected this out mathematically where Vc of t. So we have considered this output where x of n, where what you call discrete time signal. It is the input of this where x of n is the discrete time signal. It is given that what you call the system where y of n is equal to 1.01 y of n minus 1 plus x of n. We will expect this y of n. Despite having the different physical origins, these systems have similar mathematical representation. Hence, it makes sense to what do you call apply. It makes the sense to study the general mathematical representation that is common to many different applications. Okay, But here the continuous time and discrete time systems is involved this type of different physical origins. The systems have similar mathematical representation is required for deciding the factor. So basic system properties, we know that one system with and without memory. The system is called memoryless if the output at any time t or maybe n depends only on the input at time. T or small n is other words independent of the input at the times before or after t or n. So if it is a memoryless, you can decide the memoryless system or memory system. The memoryless system where if it is we can represent in mathematically where y of t is equal to Rx of t, or where y of n is the output response of this, where y of n is equal to 2r of n plus x square of n square. Like this in invertibility and inverse systems, where a system is called invertible if it is produced distinct output signal or distinct input signal. Here, if the invertibility system produces the output of y of t, for the input is x of t. That is, here it is the continuous time signal. Okay, the output is y of t. So for the input is continuous time signal. Here it is continuous time signal. Where output response is also continuous time signal. Then it is inverse produces the output x of n for the input y of what you call for the input y of t. Okay, so like this invertible system. So what's that invertible system? So if a system has a unique relationship between its input and output, the system is called the invertible system. Okay, so in other words, a system is said to be an invertible system only if an inverse system exists, which when cascaded with the original system produces an output equal to the input of the first system. We can decide the factor here, invertible system, we can define, we can observe the thing. Okay, so we have that block diagram. Based on the block diagram, we easily can understand, easily can investigate, or maybe you can interpret this all invertible system. Okay, so here within this is the block diagram where x of t or x of n, it is given to the system operator t. We will expect that all output is where y of t, y of n. So that y of n or y of t is given to that system operator inverse t inverse. We will expect that all output is y dash of t is also equal to x of t, or maybe y dash of n is equal to x of n. Yeah, mathematically an invertible system is defined where x of t is equal to, so you can decide that where x of t is equal to, so t inverse of y of t. So it's also equal to x of t is equal to y of t for discrete time system. Of that we can decide that discrete time system. Okay, like invertibility and inverse system. So under this, just now we have verified that invertibility system. Yeah, coming to this non-invertible system. So a system is said to be a non-invertible system if the system does not have any relationship between its input and output. Okay, in other words, if there is a many there is in a many to one mapping between input and output at any given instant for system, then the system is known as non-invertible system. Yeah, easily you can compare that invertible and non-invertible system. Okay, just now we have verified that invertible system, and compared to that one, in non-invertible system, a system is said to be a non-invertible system if the system does not have any relationship between its input and output. or we can consider it if there is a many to one mapping between input and output at any given instant for the system, then the system is known as what do you call uh, non-invertible system, or we can consider that what we call inverse system, where inverse system is nothing but invertible system. Okay, mathematically a non-invertible system is represented as, okay, so where x of t not equal to t inverse of t of x of t for continuous time system. Here for continuous time system. Previously we are learning that same continuous time signal. For input purpose they are the signal, but for verifying the output response we require that all system. Based on the system may be invertibility or non-invertibility or inverse system. Consider this either it is invertible system or maybe inverse system. Okay, that means for a continuous time system. Okay, so where x of n not equal to t inverse t of x of n for a discrete time system. Okay, but here it is. Compare this one and this one. Which one is how it is deciding the factor? Where x of t not equal to t inverse of capital T of x of n for continuous time system. Here it is continuous time system. Coming to the discrete time system, where x of n not equal to t inverse of t of x of n. Okay, now it is formed for discrete time system. Like this, we'll interpret this mathematically. A non-invertible system is represented as what we call continuous time system and discrete time system. Okay, you are right to verify that block diagram. We have that block diagram representation of non-invertible system shown here, where x of input is x of t or x of n. Because of we are ready to verify that either it is continuous time signal or maybe a continuous time system or maybe discrete time system. Based on these target, so we have to consider the x of t, that x of t or x of n given to this system operator t. We will expect that all y of t or maybe y of n, where y of t is followed by continuous, what we call continuous time system. If the y of n is, we will expect that all discrete time system. Okay, so that continuous time or y of t or y of n is given to that system operator because t inverse. We will expect that y dash of n not equal to x of t. Y dash of n not equal to x of n. Using the simple block diagram, you can decide the factor non-invertible system. How it is varies, how they are calculated the continuous time system and discrete time system variation or system responses. Okay, here we know this all are okay. Next, coming to the causality, the system is called the causal, or you can consider non-anticipative. The output at any time t or n depends only on the input at times t or before t or n or before n. In other words, independent of the input at time after t or maybe or n. So all memoryless systems are causal system. It is the valid point. All memoryless systems are causal system, or you can consider non-anticipative system. Physical systems where the time is the independent variable or causal. Yeah, non-causal system may arise in application where the independent variable is not the same, is not the time, such as the image processing application. So always they are using the causal variation, causal systems. Non-causal system may arise in the applications where the independent variable is not the time, such as what you call the image processing application. So application of this our DSP is the major one is image processing, where DSP, digital signal processing. So we are concentrating on one dimensional case application of the DSP, so where in image processing application we are trying to verify the two dimensional. Okay, this is the major application. DSP is image processing. Okay, for example of the causal system, y of t is equal to 1 by c integral minus infinity to t x of tau into d tau, or maybe y of n is equal to x of n minus 1. Like this, the causal system, how it is varies, how we are what you call how it is affected with these different applications are involved or not. We can decide the factor using this system is called the causal or non-anticipative system. Causal system and stability. So examples of the causal system we can represent a mathematically. We know that all y of t is equal to same, y of n is equal to x of n minus 1. Example non-causal system where y of t is equal to x of t, or we can consider that y of n is equal to 1 by 3 x of n minus 1 plus x of n plus x of n plus 1. So like this, a system. So the stable system or stability. The stability, a system is called the stable if it is produce the bounded output for all bounded input. Okay, here a signal x of t is bounded if for some m less than m less than infinity x of mod x of t less than m for all t. The stability is in physical system. Generally, we will expect that our results from the presence of the mechanism and that dissipate the energy, such as the resistors in a circuit, friction in the mechanical system, and so on. In real-time aspect, we will apply this. So the system is stable or unstable. You can decide using this all what you call it produces bounded output for all bounded inputs. How we are using this? A signal is the signal x of t is bounded if for some m less than or equal to infinity mod x of t less than or equal to capital M for all small t. Okay, so like this, such a what you call stability in the physical system generally results from the response or presence of the mechanisms that dissipate energy. So, such as the resistors in the circuit, like electrical engineering or electronics and communication engineers, they will expect, they will verify, investigating this type of system or their desirable system may be stable or unstable system. They will decide. Okay. So like this time invariant, the system is called time invariant if the way it responds to input does not change over the time. So obviously the system is called the time invariant if the way it responds the input does not change over the time. How we are deciding where x of t as to y of t. So for any t naught or for any n naught, based on that what you call either continuous time signal or maybe using the input either CTS or continuous time signal or discrete time signal. The system is called in time invariant if the way it is response to the inputs does not change over the time. Example of time invariant system like using the electrical circuit, the RC circuit considered early provides the value of R and C resistor and capacitor all constant. Okay, the time where y of n is equal to the output response is equal to x of n minus 1. Yeah, example of the time varying system, the RC circuit, resistor capacitor circuit considered earlier. If the value of R and R or resistor value or capacitor value change over the time, it is followed by y of t is equal to x of 2 into t, since x of t tends to x of 2t, but x of t minus t naught to x of 2t minus t naught. Like this, the time invariance system is called time invariant if the weight response to input does not change over the time. Okay, time invariant, we graphically we write to verify this time variant where t versus x1 of t or t versus x2 of t, and t versus y1 of t or t versus y2 of t, t versus y2 y1 of y1 of t minus 2. Using the solve value time variant, most physical systems are slowly time varying due to the hastening, hence they can be considered time invariant for certain time period in which its behavior does not change significantly. That's why always there is time invariance. You can consider that all x1 of t value, x2 of t value. The t is varies, that are what you call like 0 to plus or minus 2 or plus or minus 1 and so on. Like this linear system, yeah, these are all we know that a linear system. Yeah, linear system and non-linear system. Yeah, mathematically we can decide the factor linear non-linear system because of we are expecting all digital designs or digital filters that linear shape or linear or non-linear time. The time we require this are linear system, non-linear systems. Okay. So due to this all, some systems are involved our case digital signal processing. Like here, system classification is involved within this LTS system is required. Okay, and we'll verify the properties of LTS system. Okay, before entering this all are somewhat major important systems we are right to concentrate. Okay, so
Like, share and subscribe. Hit the bell icon for more updates.